Okay, so this is on logistic growth. I'll explain this a little bit more in a little while, but we could start off with a related rate problem, the rate at which a population grows. So it's a dp/dt, and this is based on the population. And so we have 3p minus p squared over 6,000 is a population that's growing. And we're trying to find a formula for population. Okay, so don't write this down, just follow along with me. All right, so I want to integrate this and find an equation for the original population. Now the problem is I can't, this would be easy breezy to integrate, but I have dp dt equals 3p minus p squared over 6,000. Remember, I've got to separate my variables. And so I'm going to move my dt over here, or let me do it this way. I'm going to separate my variables and go dp is equal to 3p minus p squared over 6,000 dt. And then I realize that I really need my p's over here. So I end up with 1 over 3p. Well, I also want to leave behind as much as I can. So, sorry, I'm going to do that first too. And so let's follow my work here. So I'm going to do it all the way out. Here, I factored out, and I'll show you why I did that later, but one thing I want to leave a lot behind. So I factored out 1 over 6,000p. All right, because I wanted to get rid of this denominator here, this 6,000. So I factored out 1 over 6,000p, and I'm also wanting to factor these have a p in common. And so when I do that, I get 18,000 minus p. And my dt is over here. So I'm going to leave the 1 over 6,000 on this side with the dt, and I moved p times 1,000, 18,000 minus p to this side. And now that throws me into integrating both sides. So this is separation of variables review. There's a lot of review going on here. And then my next step is this is factored. P times 18,000 minus p is factored right here. And so now my next step is partial fractions because the bottom is factored. And so I said a over p and b over 18,000 minus p. And then I did what we've just learned with partial fractions. So I multiplied a by, to get a common denominator, 18,000 minus p. And I multiplied b by p. And I set it equal to the numerator, which was 1. And so I went through what we've done with partial fractions, where I let p be 18,000, and I also let p be 0 right here. And so I got a and b to be 1 over 18,000 right here. Then I factored out the 1 over 18,000 to the outside, and I had this integration to do. So I have 1 over p, oh, and this is dp. I think I kept writing dt for some reason. I changed it, sorry. When I read it earlier, these should be dp's, because that was the whole reason I did it. The integral of 1 over p is ln p. And I had to do a substitution here going backwards. It had a minus p, so I needed a negative. So I had minus ln of 18,000 minus p. And on this side, when I integrated this side, I got 1 over 6,000 t. So I have this as my answer after I integrated it. So once again, I separated my variables. And then I factored this side. And then I moved all my p's over here, integrated both sides, and that's what you see all down here. All right, so then I multiplied both sides by 18,000. So it got rid of it over here, and the 18,000 over here gave me this 3. And when you integrate right here, I may have covered over it, that should have a plus c. So now I have this in my flow of integration, and then if they're subtracted, I can divide. You've done all of this before, okay? Then the next slide, where was I? I was right here. Okay, that's where I left off on the last slide. Then I have e to the 3t plus c equals this. And then we've talked about e to the 3t plus c is the same thing as e to the 3t times e to the c. Or you can just call e to the c just another constant of its own right here is equal to. So e to that power equals this. And then I multiplied both sides or cross multiplied and got this. And then I distributed. And then I moved this over here with the p. And then I factored out a p because our whole goal here is to solve for the population in terms of time. So now I finally have the population in terms of time. And I could leave it like that. And c is a certain constant that we could find in just a little while if we had an initial value. Right now we don't have a point to fill in. So here is my answer for population. Or some people, and actually this is what they're dealing with in our world today right now. They're looking at, this is what logistic growth equations look like when they do grow exponentially and level off. But anyway, some people take this and divide the top by e to the 3t and the bottom by e to the 3t. If you divide the top by e to the 3t, c e to the 3t, it leaves you 18,000. And then if you divide this by c e to the 3t, it leaves you 1. And then if you divide this by c e to the 3t, it leaves you c e to the negative 3t. So anyway, that's the original equation. And now I want to know my limiting factor. So I take the limit as t approaches infinity. And since it's bottom heavy, the limiting factor is 18,000. Notice this note that I had written in previous class. That's why I already have these notes done. But we already knew the limiting factor. So here's the good news. Let me see if I can move this and give you the good news. Trying to move this. Sorry. Oh, boy, that's not working. I'll move something else. I'll go to this slide. And so, good news. There it is. Smiley face. The good news here is what I had told another class before. Sorry, let me get rid of that little mark. Well, okay. I said, here's an example of integrating to find the logistic equation. Sorry, I'm having trouble. Okay, here's an example of integrating to find the logistic equation. That's what people used to do until they noticed a pattern. They used to do that whole 2 pages of work I just did. This involves integration by parts, which I did, but this is not necessary since we notice the detail but we need in this. So we have everything we need already in the derivative. Let's look back here in this mess. At the very beginning of this, I had taken dp dt, get another color. I had taken dp dt that I was given, and I had factored it. And what people have found is if you factor it correctly, your limiting factor shows up right there. So I don't even have to do all of this. People have noticed that pattern. But I wanted to do it with you at least one time to prove to you that all of this works. Because after all of this and this integration, at the very end, I actually took the limit as t approaches infinity and got 18,000 as the time grew and grew and grew. Weeks and days go by, it's going to hit about 18,000, give or take some. And so that's where we're looking for it to level off. All right, so we don't have to do that. What we want to do is this. All right, so this is what you'll do. Okay. Logistic growth. All right, logistic growth is, usually people think of it as something that levels off. But if your limiting factor, That's your horizontal asymptote, your limiting factor. If your limiting factor is like 100 and you put like 20 fish in there, then it has time to grow before it levels off. But if you put like 80 fish in there, they can reproduce and grow up to about 100, but they don't have time to grow rapidly. They're just going to like grow into the environment. What's going to happen if you put 200 fish in there is they will actually die off because it can't sustain it. So all three of these are logistic curves. It depends on where you put your initial population. Okay. So in exponential growth, we assume that the rate of increase of a population at any time is directly proportional to the population, which many times is true. This is a direct proportion. So I'm saying the rate of growth of the population is directly proportional to the population, and that gives me some constant k. And then I multiply by it, and I get pk, or we actually call it kp. But in some situations where you have a limiting factor of, let's say it was temperature of 78 degrees, and your room is starting to warm up after being really cold, it's going to still hover around 78 degrees. And so what happens is in many situations, we find things have what are called a carrying capacity because of limited resources. In this situation, the rate of increase, and by the way, you should be following along in your notes that I sent you, or you can just look at this, is directly proportional to both P and L minus P. And so you get a proportion like this. The rate of growth, they found, is directly proportional to a population if it has a limiting factor, which in reality all populations would. So this is a direct proportion, and then they multiplied it times this side. Now, this is what you need to memorize, and you can do everything with it. And then we can find the second derivative and find out how fast it's growing, how fast the virus is growing, the population is growing, or whatever it is that we're talking about. So super important. If we do this, we know L right away. This is our carrying capacity. Like how much can it carry? Carrying CAP capacity. It's also called a limiting factor. Wow, isn't that great? Because now I don't have to actually separate my variables and put my p's on one side and my dt on the other side and integrate using integration, using partial fractions. I think I said integration by parts, using partial fractions, and go la-di-da-di-da just to find the equation for population. They found a pattern. I can just do it all off the rate at which the population's growing. So our limiting factor is going to be right here. And this is going to be our different numbers for our population. We can also find out when the population's growing the fastest. And so I'll hang on just a minute. Let me look at my notes. All right, so let me tell you some about that in an extra slide. So you're going to know this big fact for logistic growth. dPTT equals Kp times L minus P. So you want this factored to where this is a constant and P is completely by itself, and then you can read this coming and going. All right, now if I distribute that, I get dP dt equals KPL minus KP squared. Let's go back to some things we did earlier in the year. I'm going to now take the second derivative of that. I think I need to write this here. Okay. All right, now at first it looks like if my variable's P, that the derivative of that would be KL. But notice every time I take derivative of P, P prime is really dP dt. So using implicit differentiation, K is going to be a constant of proportionality, L is a limiting factor, and the derivative of P is 1, so I have KL, but I have to follow it with like Y prime, which is dP dt, minus 2KP dP dt. All right, now I'm going to factor out a K and a dP dt, and that leaves me L minus 2P. All right, now I'm going to look for my point of inflection. All right, so my point of inflection, you set this equal to 0. Well, these won't equal 0 because those are going to be constants. If I set L minus 2P equal to 0, I find out L equals 2P, or P is L over 2. So we find out this real cool thing. Our point of inflection is always going to be half of the limiting factor. Okay, so that's super important, and that's quick. So I can tell when something's growing the fastest, because what happens is, what's going to happen is we're going to find our limiting factor. We're going to have an initial population, and it's going to grow, and at some point it's going to be growing the fastest, which again they're talking about in the news like crazy. And so we want to know when it's growing the fastest. Everybody's saying we're going to have a really bad week this week, until it takes a downturn and it levels off and they can let us back into our real life. One thing to look at is if this thing is increasing, its first derivative, this whole thing would be positive. Okay, and then if I do plus minus chart at my point of inflection, whatever that number is, this number L over 2, or let's look at it this way. If I have L minus 2P, if I want to see where that's greater than 0, it's when my limiting factor is greater than 2P, or when my population is greater than L over 2, which is not really what I wanted to do. I was going to maybe do a plus minus chart. But when my population is more than the, I'm not explaining this very well, just a minute. I'll do it with numbers in just a minute. I'll do a problem with numbers and it'll be more explainable there. So let's actually do like a hands-on problem. But as we leave this slide, this is ultra important. dP equals Kp times L minus P. All right, so next slide. All right, so what are we going to do with that? Oh, wait. Let's see. Oh, yeah, okay. So we have, I don't think we can see all of this. There we go. And you'll have these, you'll have these notes to you by the time you get this video. All right, so here's the population of fish in a lake, P of T, satisfies the logistic differential equation, or the derivative of the populations, the rate of growth of the populations right here. But I desperately want to get it into dP over dt equals Kp times L minus P. Okay, so what you want to do is you want this P to be by itself, and you want it to have no coefficient if you look at that. And so I've got to pull out the 1 over 6,000. So I have dP over dt. I'm going to pull out 1 over 6,000 P. Okay, when I do that, it leaves me a P in the back. And what does it leave me in the front? If you say 3 and you're dividing out 6,000 to figure out what this number is, you could just multiply those and you would get 18,000. If you're suspicious, this was the one that I like fully crazily integrated a minute ago. All right, so you can double check and see if you did it right. Your little factorization, our mistakes will probably be simple mistakes. If you redistribute, 18,000 over 6,000 is 3P, and this would give me minus P squared over 6,000. You have to do whatever it takes to get an L minus P in here. All right, so my limiting factor is 18,000. So let's say if they put in 4,000, all right, halfway is 9,000, so 4,000 would be down here. You see it's got room to grow logistically. They're all logistic. It's got room to have a point of inflection. It's got some room to grow because 4,000 is pretty far down. But the question is the solution, first of all, what is the limit of P of T as T approaches infinity? That looks like I have to integrate this and actually find P. But what's cool is I don't have to go through that whole 2 slides. I can just look over here, and if I can get it in this form, my limiting factor is voila, 18,000. In fact, this is the limiting factor of this population. I don't care what they start me with. It doesn't matter how much they put in there. This is the carrying capacity. Now, is the solution curve increasing or decreasing? Well, if it can hold 18,000 and we put in 4,000, just by common sense, it should be increasing. But also, if we look at our first derivative right here, if we look at our first derivative, I don't even think I need to do a plus minus chart. If I put in 4,000 for, let me change colors. If I put in 4,000 right there, this part's going to be positive, and this is already all positive. And so my first derivative, dp dt, the population growth is greater than 0, and so it's increasing. All right. If I put in 10,000 into, and this still fits this population of fish in a lake, the limit as t approaches infinity. I don't care how many you put in, it can only hold 18,000. So it looks like they're giving you a whole new problem, but they're not. Is it increasing or decreasing? Well, if I put in 10 and it can hold 18, it will definitely be increasing. But we can look at this again in calculus. The first derivative, if I put in 10,000 right here, 18,000 minus 10,000 is still greater than 0, and so it's increasing. So here's 18,000. Here's half of 18,000 is 9,000. So on this one, they put in 10,000, and so it didn't have much room to grow. It leveled off pretty fast, and that one would only be concave down, whereas this one is concave up to 9,000 and then concave down. So let me talk about that for a minute. The point of inflection, the greatest growth rate, it'll be growing the fastest at half the limiting factor. So I already knew my point of inflection would be this halfway point at 9,000, and this is my carrying capacity. So it's concave up before and concave down after. If I put in something after 9,000, like 10,000, it only has room to grow a little bit, and so you've already put it in past the point of inflection, so that happens. Now, if you put in 20,000, you're putting something up here. Where's black? You're putting something up here, and so it'll grow like this. All right, so I don't care how many you put in, the limiting factor of this problem is still 18,000, which is awesome that we don't have to actually separate our variables and integrate. Now, is the solution curve increasing or decreasing? It's decreasing by common sense. They're going to die off. However, I can actually enter it with calculus, because now you see right here that if you put in 20,000, 18 minus 20,000, all of a sudden your derivative is going to be negative. So it's definitely decreasing. All right, now let me see if it asked anything else here. I can check my notes. Okay, sketch the solution curves is the next part of this. If I move it up, or it must be on the next page. Let me see what I've got on the next page. I may have left that part out. All right, so the D part is in your notes, but I didn't put it in this slide. It said sketch the solution curves, and so let me put a new slide up there. So the D part is sketch the solution curves. All right, so we have this. 18,000 is our limiting factor. The solution curve for A, if you put it in at 4,000, would look somewhat like this. If you put it in at 10,000, a little up right down here, it'll look like this. And if you put it at 20,000, it'll look like this. All right, which has an inflection point? A is the only one that has an inflection point, because it's the only one that went under the L over 2, which we know is the point of inflection, which I know I proved really fast, but it is true. All right, now let's look back at dp dt multiplied out of this problem. It was 3p minus p squared over 6,000. And I factored it. I pulled out everything I could out of this, leaving a p behind. So 1 over 6,000 p left me 18,000 minus p, and that's dp dt. And I'm going to take the second derivative. So I have dp dt equals 3 minus, when you bring your 2 down, you get 2p over 6,000 of p over 3,000. But after each one of these derivatives, you should stop and say dp dt. I'm sorry, this is the second derivative. And so you're using implicit differentiation. Right now, p is like a y, dy dt, so this is like y's. That's why I'm stopping to say y prime or dp dt. All right, now look what happens if you put in 9,000. If I put in 9,000 right here, 9,000 divided by 3,000 is 3. So I get 3 minus 3. My second derivative is equal to 0. So it looks like 9,000 is a point of inflection. If you put in something bigger than 9,000, like 10,000, 10,000 is going to make this happen, okay? And 10,000 over 3 is bigger than 3. It's 3 1/3, I think. And so this is going to be negative if I put in something like p is 10,000. And this is still positive because dp dt at 10,000 we can see is still positive. So if I put in 10,000, I would have a negative times a positive. So my second derivative would be negative, which means at 10,000 should be concave down. Now what if I put in 20,000 or something over 18,000? If I put in 20,000, my first derivative is going to be negative and it will be decreasing, okay? And my second derivative, this part, you can double check, will be negative also. And this part is negative, which makes it a positive, which fits with concave up. As you see me do more problems, though, we're not going to have to do that much to it. All right, now let's go to this one. All right, and then I'm going to do your homework pages. I think is the next thing we're going to do. Okay, this one, it was horrifying at first, and I don't actually think they'll ask you this, even though it came from AP material. I haven't seen them ask this on AP exam in a long time, but I'm going to show you how to do it anyway, just in case. You never know. All right, because logistic is reported to be one of the topics on the test. They say if p of 0, if your initial population is 50, solve for p as a function of t. Normally for us, unless we're doing logistic growth, and they'll use the word, they'll let you know you're on a logistic problem, okay? If you're on another problem, to find p, you're going to have to separate your variables and integrate and go through differential equations, separation of variables to find the solution. But you saw that took me 2 slides to do that, a whole page of work actually on a piece of notebook paper. So it's all right. In fact, people that know about logistic, they know some tricks to actually go straight to population without all of this work. See if I can get to that. Okay? Big mess. Like we know a way to get to it without all of this work. All right, so let me show you how to do that. Let's see how much of this I can erase in notebook. So you're not, you will have to separate variables, I would think, on the exam. I would expect that, and we've talked about it a lot. But if you're in logistic, don't find yourself separating variables. All right, here is my dp dt. They told me dp dt equals, I got it factored into 1 over p. Sorry, I'm not writing what they told me. Here it is. You want to definitely get your dp dt into this form. All right, so dp dt, we've gotten it into this form every time we're given one. You're lucky many times they give it to you on a silver platter, like they hand it to you in this form. Kp times L minus P. All right, so the trick to find population without all of this work is you're going to always put the limiting factor is going to go on the top, times e to the something. All right, on the bottom, you're going to have another e to the something that we're going to talk about. All right, now you're going to want a number right here. And so to find that number, I'm sorry, I want to make sure I'm telling you right. To find that number, you multiply these two things together right here. I'm sorry, to find your coefficient of t, you multiply these two things together right here, and that'll give you e to the 3t and e to the 3t. And then you want to know what this number is right here that I've underlined. And the way to find that number is you're going to say the limiting, your population, let's see how I'm going to say it. Okay, your limiting factor minus the population you start with over the population you start with. We'll do this a few times. In this case, my limiting factor is 18,000. And the fish problem a second ago, we started with 4,000. And we put it over 4,000. And so I have 18,000 minus 4,000 is 14,000 over 4,000. These reduce. And here I get 7/2. And then I would multiply, by the reciprocal. Not the reciprocal. I would multiply to fix up that complex fraction. I couldn't think of the word. Okay, so this one I'm not going to finish, but I'm going to show you where we ended up. We ended up with, and I know it looks a bit different. Let's see. We ended up with, oh, sorry, I keep forgetting to, there. We ended up with this right here, okay, which is a little bit different than what we have on the other slide. But once I know my initial population, I would find this C, which would lead us into what we have. So I'll be showing you that on a more specific one. But the good news is that there's a way to actually get that equation, and we will definitely be doing it. Okay, so having said all of that, let's definitely do one. Okay, so that's maybe too much rambling. So let's just out and out do it. Okay. Somehow I lost my, there we go. All right, so now I'm going to write the population. All right, notice that they gave it to me already factored into Kp times L minus P. Just a minute, I'm looking at my notes. Okay, so my limiting factor is 3,000, and I have e to the something t over a number plus e to the something t. All right, the way to get this coefficient of t is you multiply these two things together. This is 1 over 1,000 times 3,000. 0.001 is 1 over 1,000 times 3,000, or if you have a calculator, you can just multiply them, and that gives you 3, e to the 3t. And then I need to know what this number is right here, and to find that number, I take my limiting factor minus the population and put it over the population. My limiting factor here is 3,000. This is L minus P. Minus my initial condition, which is 50, my initial population over the initial population. And so that gives me 2950 over 50. And I believe that's 59. 2950 over 50 is 59. All right, now this is a P of T, population in terms of time. That just is a little cumbersome, but it took the place of 2 pages of work. This would be what I would get if I went through separation of variables, integration by partial fractions, and so on. And so I like this better. It's worth remembered, and I'll do it a few more times with you. Now on B, use your solution to find the size of the population in 2 days. They were starting to ask me specifics, and so I had to find the initial population. I want to fill in 2. And then I want to use this solution, so I had to know the original this time. I didn't have any tricks to answer these type of questions. To find the number of days that occurred when the flu is spreading the fastest. Again, the rate at which a flu spreads through a community is modeled by this logistic equation. It's happening in our world right now. All right, so this is cool. I've got a really awesome calculator on my iPad. And I think this is the newest version. Yeah, okay. And so I'm going to go to my whiteboard, and I'm going to put in 3,000 e to the kt. So I'm going to, it's just like my calculator, e to the 3x. Move out of that, divided by parentheses. The bottom was 59 plus e to the 3t, or 3x in our case. Okay, and I'm going to get rid of this number. Okay, now my window, usually it doesn't take much time for this to happen. Think how early we are in our progression of the worldwide pandemic. So I'm going to only, X is time right now. I'm going to go out from like 0 to like 5. I'm not going to go very far because this grows really fast. My Y-min is 0. I know my limiting factor, whatever this equation is, shouldn't pass my limiting factor of 3,000. And the rest of that doesn't matter. So now I'm going to graph, and you see this nice logistic curve. And now, let's see, I can go to table. And I haven't actually tried this, but I can put in 2. I imagine I can set table. I don't know if it lets me put my own input in, actually, but anyway, it's pretty cool. So let's go to table. Oh, and I did see 2 just a little while ago. Yeah, I guess you could change the, I don't know, there's probably a better way that I don't know. I just loaded this today. So at 2, you can see we have 2,617 people have the flu. I don't think I can write on the screen, but it's right. Let's see, right in here. All right, so 2 is right where you can see it, 2,617. All right, so the answer to this would be, so you would go to table and just fill in 2. 2,617 people would have the flu after 2 days. After 2 days. Use your solution to find the number of days that have occurred when the flu is spreading the fastest. All right, so how can I use our little tricks here to find out when we could definitely see it was spreading the fastest somewhere in there. But I already know my limiting factor is 3,000. And so I know on the C part is spreading the fastest when the population at some time is equal to half the limiting factor, which is 1,500. So I'm going to go into my calculator, and I'm going to put in half of 3,000, which is 1,500, and I'm actually see it hit that limiting factor. Again, you see this all over the news right now. Like in the version I have, it has a form of calc intersect that locks into that for me. And you can see it up at the top of the page. It happens when X is, I don't know if you can see it at the very tip top. I don't think I can move my page, but if you look at the very tip top, it happens when X is 1.359. And so this happens when the time is 1.359 days is when the population is growing the fastest. And again, you could look at all of the stuff we talked about. Before that, it would be concave up. After that, it's concave down, and so on. All right, so I'm going to stop this video. In the next video you get, I'm going to be doing the homework.